All right, as we get started with looking at energy sources found throughout the world, we need to first define what is energy. When we talk about energy, it's the ability to do work. It comes from many sources and in many forms. The forms of energy are classified into two general categories, potential and kinetic. Potential energy is energy stored in an object. Chemical, mechanical, nuclear, gravitational, and electrical are all stored energy. Kinetic energy does the work. Light, heat, motion, and sound are all examples of kinetic energy. Here's a simple example to consider. Stretching a rubber band gives it the potential to fly. The tension created from stretching is the potential mechanical energy. When the rubber band is released, it flies through the air using motion, or kinetic energy. The process of changing energy from one form into another is called energy transformation. The rubber band is transformed from potential energy into kinetic energy. Systems convert energy at various rates of efficiency. Water turbines, for example, are very efficient, while combustion engines are not. Engineers and physicists constantly work to develop systems with high energy conversion efficiency. As you can see, there is a variety of energy sources that are currently in existence. We have hydroelectric, natural gas, petroleum or oil, propane, hydrogen, solar, coal, nuclear, wind, geothermal, and biomass. Engineers are primarily responsible for the research, development, and design of the equipment that captures energy from renewable and fossil fuel resources for human use. Given the eventual decline in the availability of these fossil fuel resources, engineers are tasked with designing technologies that can capture renewable energy sources that are more efficient, more reliable, and economically competitive. As we classify energy sources, primary energy sources can be basically classified into two groups, non-renewable and renewable energy sources. Secondary sources are derived from primary sources. Non-renewable sources have a definite, limited supply of source of energy, and it cannot be replaced once used. Renewable energy sources, on the other hand, have a source of energy that can be replaced as we use it. Energy from the ground that has limited supplies in the form of gas, liquid, or solid are called non-renewable resources. Fossil fuels are great examples of non-renewable resources. Fossil fuels are found deposited in rock formations. They were formed between 350 million and 50 million years ago. The processes by which they were formed are not totally understood at this point. Decayed remains of ancient plants and/or animals were buried through the sediments. Through the action of heat and pressure over millions of centuries, they were chemically changed. Coal, oil, and natural gas are all results of this process. Most of our energy needs are currently met by fossil fuels. These renewable energy sources take millions of years to form, and they cannot be regenerated in a short period of time. All right, as we dive deeper into our look into natural gas, make sure you watch this video as it walks you through kind of the process of how natural gas is formed. But I did want to provide you with an overview. So natural gas is a fossil energy source that formed deep beneath the Earth's surface. Millions of years ago and over long periods of time, the remains of plants and animals built up in thick layers on the Earth's surface and ocean floors. Sometimes it was mixed with sand and silt. Over time, these layers were buried under the sand, silt, and rock. Pressure and heat changed some of this carbon and hydrogen-rich material into coal, some into oil or petroleum, and some into natural gas. Make sure you understand that natural gas should not be confused with gasoline, which is a petroleum product. Natural gas from underground reservoirs is a non-renewable energy source, which means we cannot make more of it in a short amount of time. Natural gas production, transportation, distribution, and storage require strict safety regulations and standards. Because a natural gas leak could cause an explosion, strict government regulations and industry standards are in place to ensure the safe transportation, storage, distribution, and use of natural gas at all times. Because processed natural gas has no odor, natural gas companies add a strong, rotten, egg-like smelling substance to its natural gas so that the people can smell when leaks occur. I do want to talk about the history of natural gas. Starting in 1626, naturally occurring natural gas was discovered and identified in America when French explorers discovered Native Americans igniting gases that were seeping into and around Lake Erie. In 1785, Britain was the first country to commercialize the use of natural gas, and natural gas produced from coal and was produced from coal and was used to light houses as well as streetlights. In 1821, in the U.S., the first commercial application of petroleum product was utilized of natural gas from a shallow well in New York. The gas was distributed through a small bore lead pipe to consumers for lighting and cooking. In 1891, the first major pipelines were constructed. This pipeline was 120 miles long and carried natural gas from wells in central Indiana to the city of Chicago. However, this early pipeline was not very efficient at transporting natural gas. Moving on to the late 1920s, advancement in pipeline technology took off, and they made long-distance gas transmission more practical. From 1927 to 1931, more than 10 major transmission systems were constructed in the U.S. And then following World War II, many longer and wider pipelines were then constructed. It's important to understand some of the uses and demand for natural gas. Most natural gas is used for heating buildings and generating electricity, but some consuming sectors have other uses for natural gas as well. For example, the industrial sector uses natural gas as a fuel for process heating in combination of heat and power systems, as well as with raw materials or feedstock to produce chemicals, fertilizer, and hydrogen. According to the BP Energy Outlook, the increase in demand for natural gas in the industrial sector is driven by developing economies as they continue to industrialize, especially in regions with large gas resources, typically found in the Middle East or Africa. Switching from coal to gas is also a larger part of high gas demand, especially in China. The electric power sector uses natural gas to generate electricity. In 2017, the electric power sector accounted for about 34% of the U.S. natural gas consumption, and natural gas was the source of about 26% of the U.S. electric power sector's energy consumption. The residential sector uses natural gas to heat buildings and water, to cook and dry clothes. About half the homes in the U.S. use natural gas as for these types of purposes. In 2017, the residential sector accounted for about 16% of U.S. natural gas consumption, and natural gas was the source of about 23% of the U.S. residential sector's total energy consumption. When looking at the commercial sector, they use natural gas to heat buildings, water, to operate refrigeration and cooling equipment, to cook, to dry clothes, and to even provide outdoor lighting. Some consumers in the commercial sector also use natural gas as a fuel in combined heat and power systems. And even more and more of the transportation sector uses natural gas as a fuel to operate compressors that move natural gas through pipelines, and as a vehicle fuel in the form of compressed natural gas and liquefied natural gas. Nearly all vehicles that use natural gas as a fuel are in a government and private vehicle fleets. In 2017, the transportation sector accounted for about 3% of the U.S. total natural gas consumption. Natural gas was the source of about 3% of the U.S. transportation sector's energy consumption in 2017, of which 94% was for the natural gas pipeline and distribution operations. When using natural gas, it's important to understand both the pros and cons of this energy source. Starting with the pros, natural gas is widely available. It burns more cleanly than coal or oil. It's often used in combination with other fuels to decrease pollution in electricity generation. It has an added artificial odor that people can easily smell the gas in case of a leak. But there are some cons to consider. Transportation costs are extremely high. It burns cleanly, but it still has emissions. And that is because natural gas is mainly methane, a strong greenhouse gas. And some of that natural gas leaks into the atmosphere from oil and natural gas wells, storage tanks, pipelines, and other processing plants, which could impact our ecosystem. As we turn our attention to petroleum or oil, it's a fossil fuel made naturally from decaying prehistoric plant and animal remains. It's a mixture of hundreds of different hydrocarbon molecules containing hydrogen and carbon that exist sometimes as a liquid, which is crude oil, and sometimes as a vapor, natural gas. Petroleum is a non-renewable energy source that is limited in quantity. Forecasts vary on how long the source will last based on many variables, including demand, cost of extracting, and increased use of renewable energy sources. Millions of years ago, prehistoric plant and animal remains settled into the seas along with sand, silt, and rocks. As the rocks and silt settled, layer upon layer piled up in rivers, along coastlines, and on the seafloor, trapping the organic material. Without air, the organic layers could not rot away. Over time, increasing pressure and temperature changed the mud, sand, and silt into rock, and it slowly cooked the organic matter into petroleum. The rock formation holds petroleum like how a sponge holds water. From ancient times throughout the early 1900s, finding oil and gas was largely a matter of luck. Early explorers looked for oil seeps at the surface and other surface signs that oil might exist below the ground. This was a haphazard process. However, science and technology quickly developed to improve the industry's ability to determine what lies below the ground. Geologists study rocks on the Earth's surface as well as underground to create maps of where they think the oil and gas might be found. Engineers use this geology map to drill a well under the Earth's surface. If it's successful, the well will bring a steady flow of oil and gas to the surface afterwards. After the drill rig is removed, a pump is placed on the wellhead. An electric motor drives the gearbox that moves the lever. The lever pushes and pulls, forcing the pump up and down, and creates a suction that draws up the oil. 3 factors affect the amount of oil or gas that's recovered from a known reservoir: rock properties, technology, and economics. While the industry cannot change the properties of the rock, it can develop new techniques to remove more oil from the rock. The industry has more significant advances to enhance recovery from these known reservoirs worldwide, adding to their reserve base. Many factors can affect oil and gas production, such as civil unrest, national or international politics, adherence to quotas, oil prices, oil demand, new discoveries, and technology development or application. The large subsurface traps are the easiest deposits of oil and gas to locate. In mature production around the world, most of these large deposits of oil and gas are already found, and many have been producing since the 1960s and early 1970s. The oil and gas industry has developed new technology to better identify and access oil and gas. Improved seismic techniques, such as the 3D seismographs, have increased the odds of correctly identifying the location of smaller and more difficult to find reservoirs. New drilling techniques can intersect a long, thin reservoir horizontally first, then it turns vertically, making an L shape. This enables the oil or gas from the reservoir to be recovered with fewer wells. In terms of the history of oil, around 3 million years ago, during the Stone Age, underground oil reserves seeped to the surface in sticky black pools called bitumen. Hunters used this bitumen or tar to attach flint arrowheads to the arrows. 70,000 years ago, prehistoric people discovered that oil burns from a bright, steady flame. The first oil lamps were made by hollowing out stone, filling it with moss, and setting it on fire. In the 1780s, a Swiss physicist realized that by placing a circular wick in the middle of an oil lamp and covering it with a chimney to improve airflow, the lamp could be burned 10 times brighter than a candle. In 1896, Henry Ford built his first automobile to run on pure ethanol. In the 1930s, petroleum is the primary source for fuel because of its major supply, cost, and efficiency. In 1950, oil becomes our most used energy source because of automobiles. In 1988, ethanol begins to be added to gasoline to reduce carbon monoxide emissions. In 2003, flex fuel vehicles are introduced, and these vehicles can run on straight ethanol, straight gasoline, or a blend of the two. While we look at the uses and demand of petroleum or oil, I would encourage you to look at the link to that poster above, as it will kind of walk you through all these different examples of how oil is used in everyday life. But keep in mind, petroleum demand has been on a steady incline for many decades now. Future predictions indicate it will continue to be the largest supplier of worldwide energy throughout the year 2050. The world currently uses about 100 million barrels of oil per day, which is 4.2 trillion gallons a day. And the world's energy needs continue to climb as economies and populations expand, especially in developing countries. Therefore, a large part of the demand still comes from the industrial sector, which includes refining, mining, manufacturing, agriculture, and construction. Transportation consumption is predicted to even increase by 40% by the year 2050 as well. There are many factors that will determine the demand and energy mix over the next 30 years or so. Sustainability programs and technology can change the landscape for the upcoming years. Oil is not just a source of energy, it is also a remarkable raw material. Its rich mix of hydrocarbons can be processed to give useful substances known as petrochemicals. Processing usually alters the hydrocarbons so completely that it's hard to recognize the oil origins of petrochemical products. An amazing range of materials and objects can be made from petrochemicals, from plastics to perfumes and bed sheets. We use many oil products as synthetic alternatives to natural materials, including synthetic rubbers instead of natural rubber and detergents instead of soap. But oil also gives us an entirely new, unique materials such as nylon. Plastics play an incredibly important role with the modern world. They find their way into our homes in many different ways and forms, from boxes used to keep food fresh to remote controls. Plastics are essentially materials that can be heated and molded into almost any shape desired. They have the quality because they are made from incredibly long chain-like molecules called polymers. But nearly all the polymers we use today are artificially made, and the majority of them are produced from oil and natural gas. Scientists are able to use these hydrocarbons in oil to create an increasing variety of polymers, not only for plastics, but also to make synthetic fibers for other materials. When we look at the pros and cons for oil, some of the pros include that it's used as transportation fuel for the world. It serves as the basis of many products, from prescription drugs to plastics. It's economical to produce, and it's easy to transport. Some of the cons of using oil is there's a high CO2 emissions. It is found in limited areas. Its supply may be exhausted before natural gas or coal resources are. And there's possible environmental impacts from drilling and transporting that oil. I did want to quickly mention another type of energy source, which is propane. Propane is really produced as a byproduct from natural gas processing and crude oil refining. It burns hotter and more evenly than other fuels. Some of the pros: it yields 60 to 70% less smog-producing hydrocarbons than gasoline or diesel fuel would. It's non-toxic and it's insoluble in water. It doesn't spill, pool, or leave any type of residue. And then some of the cons: it uses some fossil fuels in conversions. It's highly flammable. It's got less energy in a gallon of propane than in a gallon of gasoline or diesel fuel. As we look at coal, I do recommend again that you watch the video of how coal is made, but to just kind of give you a brief overview, coal is a non-renewable energy source that takes millions of years to create. It's a combustible black or brownish black sedimentary rock composed mostly of carbon and hydrocarbons. The energy in coal comes from the remains of prehistoric plants and animals, making it part of the fossil fuel family. Coal formation began about 280 to 345 million years ago. Much of the earth at this time was covered with swamp, and large amounts of plants and other organic matter grew. But as the plants and other life forms died, they sank to the bottom of the swampy areas. They slowly decomposed and they formed peat, a soggy, dense, sponge-like material. Over time, the peat was buried and compressed under the Earth's surface. As the Earth's surface changed over millions of years, sand, clay, and other materials accumulated, burying the peat. As layer upon layer was created through heat and pressure, it compressed the peat into the hard substance we call coal. Some coal beds lie within 200 feet of the Earth's surface, while deeper coal beds can be found up to 1,000 feet below surface. Coal reserves are found in almost 70 different countries worldwide, and according to the World Coal Association, more than 1.1 million tons of proven coal reserves are currently available internationally. It's estimated that the worldwide proven coal reserves are enough to last 150 years at its current consumption level. Finding coal reserves is a long process that involves exploring, mapping, and drilling. It often starts with the creation of a geological map of an area that may contain coal reserves. Then geochemical and geophysical surveys are carried out and exploratory drilling takes place. The area will become a mine if it's proven to contain usable coal that can be recovered economically. Coal can be extracted through the surface, which is called open cast mining, or underground, which is called deep mining. The method used is determined by the geology of the area. Surface mining recovers a higher percentage of the coal deposit than underground mining does, but it is only feasible when the coal deposit is near the surface. Underground mining is used to extract and accounts for about 60% of the current world's production. As we look at the history of coal, back in the 1300s, the Hopi Indians in what is now the U.S. Southwest used coal for cooking, heating, and to bake the pottery they made each and every day from clay. In 1769, Scottish engineer James Watt invents the steam engine. It used coal to make steam to run the engine. In the 1770s, the English find that the coal could produce a fuel that burned cleaner and hotter than wood charcoal. In the 1800s, the Industrial Revolution spread. People used coal to manufacture goods and to power steamboats and railroad engines. In 1882, Thomas Edison builds the first practical coal-fired electric generating station, supplying electricity to some of the residents in New York City. In 1961, coal becomes the major fuel used by electricity utilities to generate electricity, and it becomes the largest source of electricity. Today, coal provides 41% of the world's overall electricity, according to the World Coal Institute. In terms of the uses and demand for coal, in some countries, coal is burned directly for heating or cooking, but most coal is used in power plants to generate electricity. Coal has many uses other than electricity. Materials that contain coal and coal coke, a concentrated form of coal that is stripped of its volatile materials, are used in many products that we see every day, including tar, perfumes, golf balls, chalk, paper clips, dyes, aspirin, soap, as well as a sugar substitute. As we look at the pros and cons of using coal as an energy source, in terms of the pros, it's got an abundant supply. It's currently inexpensive to extract, and it's a reliable and capable of generating large amounts of power. However, coal mining and coal use has historically had a negative impact on the environment, particularly by creating harmful gases including CO2 and methane. But the coal industry is working to improve these detrimental effects. Coal mining's effect on the environment does reach beyond the atmosphere. In fact, the earth feels it as well. On land, coal mining can lead to soil erosion and dust, and it distributes large tracts of land in general. In water, acid mine drainage, a metal containing water that is formed by a chemical reaction between water and rocks containing sulfur-bearing minerals, can pollute the water around a coal mine. With plants and animals, coal mining, particularly surface mining, can disturb land that is used for grazing, animal habitats, forests, crops, and more. But the coal mining industry is making efforts to rehabilitate the land once the mining is complete, and it's their top priority. After mining is complete, companies will come in and reshape the area, replace topsoil, replant vegetation, and make the reclaimed land suitable for wildlife, agriculture, and more. As we look at uranium, our last non-renewable energy source for today, think of uranium as basically nuclear energy, nuclear power. Nuclear energy is energy in the nucleus, or core of an atom. Atoms are tiny particles that make up every object in the universe. Bonds that hold atoms together contain large amounts of energy that's released in the form of heat in two ways: nuclear fusion or nuclear fission. In nuclear fusion, atoms release energy as they are combined or fused together to form a larger atom. For instance, this is how the sun produces energy. Fusion creates energy with less radioactive material, but it's harder to control the reaction. Scientists continue to work on controlling nuclear fusion in an effort to make a fusion reactor to produce electricity. Nuclear fission is the process of splitting apart uranium atoms in a controlled manner that creates energy. If the chain reaction of splitting the atoms is not controlled very carefully, an atomic explosion could occur, although the conditions must be perfect for an atomic bomb to occur, and these conditions are not present in nuclear reactors. The fission process gives off heat energy, which is used to boil water in a power plant's reactor core. The steam created with this water is used to turn a turbine, generating electricity. Physics and chemistry played an important role in the discovery of nuclear fission, and today's physicists and chemists work together with engineers to make nuclear power possible. Expertise in physics and chemistry are critical to controlling the chain reaction of splitting atoms. As we look at the development of uranium throughout history, it's important to note that nuclear energy is relatively a new energy source. It was discovered in the 20th century, unlike fossil fuels, which have been around for millions of years. So back in 1900, physicists discovered that the atom contains large quantities of energy. In 1934, physicist Enrico Fermi conducts experiments in Rome that show neurons could split into many kinds of atoms. In 1942, Enrico Fermi and Hungarian physicist Leo Szilard create the first manufactured reactor, known as Chicago Pile 1. Most early atomic research focused on developing an effective weapon for use in World War II under the code name the Manhattan Project. In 1951, electricity is generated for the first time by a nuclear reactor in the U.S. In 1958, construction begins on the world's first nuclear-powered merchant ship, the NS Savannah in the U.S. The ship launched on July 21st, 1959. And at the end of 1991, 32 countries had nuclear power plants in commercial operation or under construction, indicating worldwide commitment to nuclear power technology. And as of today, I believe there's about 99 reactors around the U.S. that are used to generate nuclear power. When it comes to the uses and demand for uranium, nuclear power is primarily used for ship propulsion and electricity generation. About 11% of the world's electricity today comes from nuclear power. Some countries even rely on nuclear energy for most of their electric power. It also plays an important role in medicine, industry, science, food preservation, and agriculture. Physicians use radioisotopes to identify and investigate the causes of disease. They also use them to enhance traditional medical treatments. Radioisotopes are also used by industries to measure microscopic thickness, detect irregularities in metal casings, and to test welds. Archaeologists use nuclear techniques to date prehistoric objects and to locate structural defects in statues and buildings. Nuclear irradiation of food, or treating food with ionizing radiation that kills bacteria and parasites, causes less vitamin loss than canning, freezing, or drying in food preservation, and it can also cut down on foodborne illnesses. Higher oil and gas prices make alternatives such as nuclear power more attractive and are expected to lead to growth in nuclear generating capacity worldwide. Improvements in reactor designs enhance safety, increase efficiency, and reduce costs, making nuclear power an economically attractive source of energy for the future. As we look at the pros and cons to uranium, there are no greenhouse gases or CO2 emissions. It efficiently transforms energy into electricity. Uranium reserves are abundant. They are refueled yearly, but some of the cons include there's higher capital costs, there's problem of long-term storage of radioactive waste, its heated wastewater from nuclear power plants can harm aquatic life, and there's potential nuclear proliferation issues. So as we continue to look at various energy sources, we've looked today at simply the non-renewable energy sources, including oil, natural gas, and coal. And although these are primary energy sources that will be used for the foreseeable future, there is a variety of resources that will be needed to meet the world's growing demand. All energy sources have benefits as well as challenges that we have to overcome. As we continue to look at the challenges that different energy sources provide, there are some things that we need to consider when selecting which energy source is going to be best to use. First, we have to think about how much it will cost to set up and operate. Second, we need to decide if the energy source requires storage and will the final product be too expensive to utilize. Third, can it be produced on a large scale? And then fourth, we need to know how the production of this energy source will have an impact either positively or negatively on the environment.